SwayamPrabha. Digital India. Educated India.
सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, this will be lecture number 45 on our ongoing series on mechanical measurements. Towards the end of the last lecture, we were actually looking at the problem of measurement of particulates in air, and we were thinking of doing a problem, and so we will start with that problem. In fact, that will also mean that we are going to complete our discussion on measurement of particulates and then move on to the next topic. So, in this lecture the problem 50 is the one which is going to come from the previous lecture, whatever is left out. Then we will look at some interesting things about measurement of force or acceleration, torque and power. The measurement of force and acceleration, torque and power are very important from the point of view of mechanical engineering applications. For example, if you have an engine or a power producing device, we would like to measure the power output, and the power output requires the measurement of a torque and the speed of the engine or the machine. In some other applications, for example, force is involved in the measurement of weight of an object, or force experienced by an object under acceleration, and therefore we may be interested in measuring force as well as acceleration independently. For example, in the case of vibration problems, one would like to measure the forces experienced by an object when it is subjected to acceleration because of the vibrating motion of the system. So, acceleration may also be involved in the measurement of, for example, when an earthquake takes place, there are some accelerations which are experienced by various objects which are on the ground, and we would like to measure these accelerations because these are going to determine whether those systems will survive or not in an earthquake. So, let us get back to problem number 50 because that is what we would like to see, and the problem is specified in this particular slide. We have a path length of 10 centimeters, and if you remember the opacity measurement, we have a light emitting diode as a source of light and a photodiode or a photo detector as a detector for energy transmitted across a path length. And as you remember, the radiant energy is going to be absorbed and possibly also scattered because of the presence of the particulate matter. So, we are interested in looking at what happens when you have such a situation. So, we have a 10 centimeter path length and the opacity of a smoky stream is given to be 40%. This is from measurement. So, we would like to find out what is the extinction coefficient corresponding to this 40% opacity. Then further we are given that the smoke density in the gas stream, after all the smoke, a small amount of particulate matter is present in the gas as a mixture, and the 600 milligram per meter cube is the total content of that. So, 600 milligram per meter cube is the amount of particulate matter present in the gas. So, we would like to find out what is the extinction cross section in meters squared per kilogram. We will work it out, and if the smoke is approximated as containing carbon particles of average diameter 0.2 micrometers, we would like to find out the absorption cross section for the particles, or extension cross section for the particles, because extension I am using as a term which includes both absorption and possibly scattering, maybe mostly scattering and to some extent absorption. So, we assume a density of 2300 kilograms per meter cube for the carbon particles. We will work out the solution on the board, and then get back to the discussion on the measurement of force and such quantities. So, we have essentially we have a source which is an LED, and there is a photo detector. I will just use the symbol PD for that, and we have a radiation going across, and this is 10 centimeters, that is the path length. So, if I say L equal to 10 centimeters, and if we assume that the intensity of radiation leaving the LED is I subscript 0, and what is measured is the transmitted. So, we know that the opacity is nothing but, in this case it is 0.4, that means the transmitted amount or transmittivity is 1 minus 0.4, which is 0.6. That means that this transmitted amount IT divided by I subscript 0 is 0.6, that is what it means. Okay. This we will write as e to the power of minus the extension coefficient beta multiplied by L. So, 0.6 equal to e to the power of minus beta times L. So, what I have to do is to find out L is known, this is nothing but 0.1 meter. So, I can work it out what is the value of the beta, that is what we would like to do. So, all I have to do is to take logarithms on the two sides with respect to natural logarithm, then you see that minus beta L is equal to logarithm of 0.6, and I can put the value of 0.1 for L, and therefore, beta will be given by minus of logarithm of 0.6 divided by 0.1, and this comes out to be 5.1083 per meter, because I am using 0.1 is 10 centimeters what is given, this is equal to 0.1 meter. So, I have taken everything as SI units. So, the extension coefficient beta comes out to be 0.1083 meters. This is the per meter. This is the first answer which is required. We also are given that the sample has got a concentration. So, the concentration of smoke, concentration is measured either in terms of the number of particles per cubic meter of the entire volume, or it could be amount of material per unit volume. In this case, what we are given is the amount of material in terms of mass per unit volume. So, we will call it concentration is measured in rho of the smoke, the density was 600 milligrams per cubic meter. So, you see that we have a very small amount of the particular material. This is actually 600 into 10 to the power of minus 3 kilograms per meter cube. It comes to 0.6 kilograms per cubic meter. This is I am sorry, this is not correct. (600) into 10 to the power of minus 3 kilograms per cubic meter, because 1 milligram is 10 to the power of minus 3. Actually, this is 10 to the power of minus 6. So, let me just correct it, because I am putting everything in terms of minus 6 kilogram per meter cube. Okay. So, what we have to do is now we can define the beta, which is the quantity we described earlier. The extension coefficient can be written as the density rho s times the cross section we will call it the sigma E, the cross section of the particulates, and therefore sigma E, actually if you remember beta is in 1/meter, this is in kg per meter cube, sigma E is in meter squared per kilogram. So, the kg will cancel, it will give you 1/meter. So, it is nothing but given by the density multiplied by the extension cross section per unit mass. Sigma E is extension cross section per unit mass. So, sigma E is beta by rho s. So, we can put it as 5.1083 divided by 600 into 10 to the power of minus 6. Units will be meter squared per kilogram, as you have seen from the workout here. This comes out to 8513.8 meter squared per kilogram. That is the second answer we require, that is the per unit mass, the extension cross section. It is in the form of an area. So, extension cross section is like what do we mean by that? It means that the amount of radiation which is removed is given by this particular cross section. It is as though there is so much of cross section per kilogram. Of course, the amount of material is only 600 milligrams per meter cube, therefore, it will be proportional to that. So, we now will look at the mean diameter is given of the particles, of the smoke particles. I will call it as dP. It is 0.2 micrometers. So, 0.2 micrometer. So, that will be 0.2 into 10 to the power of minus 6 meter. To the power of minus 6 meter. So, we can find out the volume per particle. So, we will see how we are going to work it out. We know the volume per particle is the volume per particle if we find out the volume per particle, then I can multiply by the density of the particle to get the mass per particle, and already I know the extension cross section per kilogram of the material. So, now I will be calculating by knowing the volume per particle, then I can calculate the mass per particle. Therefore, I can find out per particle what is the cross section. That is the idea of this calculation. So, volume per particle is given by pi by 6 dP cube, that will be pi by 6 into dP cube is 0.2 into 10 to the power of minus 6 whole cube. This will be in meter cube, and this works out to 4.189 into 10 to the power of minus 21 cubic meters. We are working with very small volumes, and the corresponding mass of the particle. Therefore, mass of particle MP is rho of the particle multiplied by Vp, and rho is given as 2300 kilograms per meter cube for carbon multiplied by 4.189 into 10 to the power of minus 21. This will be meter cube. So, that will give you the mass of each particle, which will be 9.6342 into 10 to the power of minus 18 kilograms. So, we are talking about very small mass for each particle, and we already know the extension coefficient, or in fact we can also find out the number density of the particles. Because we know the amount of material present per unit volume, I can find out this is given in 600 milligram per meter cube. So, I know the volume mass of each particle I know, therefore, I can find out the number of particles. So, simply given by rho n p, the number of particles per cubic meter, that is the number density, is given by the density of the smoke divided by the mass per particle. So, this rho s is 600 into 10 to the power of minus 6 divided by what we found out just now, 9.6342 into 10 to the power of minus 18. This will give you a number density of 6.228 into 10 to the power of 13 per cubic meter. So, number of particles per cubic meter is actually a large number like 10 to the power of 13, almost 10 to the power of 14. So, the extension cross section we can calculate now per particle basis. Can also be calculated. It is simply given by sigma extension coefficient per particle is beta, which is per kg, multiplied by the mass of each particle. So, you see that you will get 5.1083 multiplied by mass of each particle we already have 9.6342 into 10 to the power of minus 18. This will be in meter squared per particle. So, per particle I do not have to mention. So, beta squared is the per particular basis, it gives you 4.92 into 10 to the power of minus 17 square meters. So, the reason why I took up this problem is just to give an idea as to the kind of numbers that describe the process we are talking about. When you have 40% opacity, that means 60% is transmitted, and if you assume the particles to be about 0.2 micrometer diameter, the absorption cross section or extension cross section per particle is only 10 to the power of about 5 into 10 to the power of minus 17 meter squared, and because the number of particles is very large in a cubic meter, you see that the absorption is quite strong or the extension is quite strong. So, with this we actually complete our discussion on the measurement of gas concentration, particulates and so on, and we now move on to the next topic which I am going to look at is the measurement of various quantities like force, stress and so on, and torque, power and things like that. Let us look at the reason why we do that. There are many interesting important applications in engineering where such measurements are required. Stress measurement of course is very important in the characterization of materials, studying the behavior of materials, mechanical behavior of materials. Forces are involved in many mechanical systems, and for design or for characterization we require to measure forces. So, let us look at the slide which shows some of the typical cases which we will meet with in practice. So, force or stress measurement is important in many applications such as weighing of an object. Just to weigh an object we require an instrument, a weighing machine, and it is usually a machine which actually uses forces or balance of forces. The measurement of force and stress are involved also in dynamics of vehicles like 4-wheelers, 2-wheelers and so on, and they are subject to a lot of forces because of the road surface, the way the road surface varies in the shape and waviness and things like that. Therefore, dynamics of vehicles means the study of forces which is subjected to because of various conditions prevailing on the when the vehicle is moving. There may be control applications. For example, in the case of an automobile, for the safety of the passengers we have airbag system. The airbag is supposed to deploy as soon as there is an indication that there is likelihood or there is a collision which has taken place, and the collision has to be actually sensed by a sensing element, and that sensing is done by measuring the force an element is subjected to, and if this force is more than certain value the airbag will deploy. So, this is the control application where the deployment of the airbag takes place only if the force is more than certain value, and this is measured by a force transducer or a force measuring device. So, there is a very important safety, it is also an important application where safety of the passengers in a vehicle are involved. Then we have study of behavior of materials under different types of loads. For example, you may have a beam which is subject to bending, you may have a ring element which is subject to compression or expansion, or for example a pipe carrying a high pressure fluid inside, it will of course subject the wall of the pipe to stresses, and these stresses we need to measure, or we need to find out what these stresses are, find out whether the safety is taken care of by seeing that the forces are less than, or the stresses are less than the allowable stresses for the material of the pipe and so on. And sometimes we also have vibration because of time varying sources, time varying forcing, and these vibration studies involve the study of vibration forces a particular system is subjected to, and also the amplitude of this vibration which the system responds to. So, we would like to measure both the vibration in terms of its frequency, in terms of its forces it induces, and also the accelerations because of that. These are the things which we need to study. And in fact, in seismology, which is the study of earthquakes, to monitor the earthquake you require a measurement instrument which will measure the acceleration or the change of, or the forces which are going to be operative because of the earthquake. So, in all these cases forces and stresses are going to be the measured quantities. Then the secondly, we are interested in torque measurement, and to just explain the measurement of torque, let me just look at the definition of torque. So, if you have a rotating system, and if you, this is the radius, and if the rotation is due to some force, so F into R is your torque. This is basically the definition of the torque. The force applied on a rotating shaft, for example, and if the force is applied with a moment arm, R is a moment arm, so the product of F and R is actually the torque. So, we can see that we can measure the force and the radius separately and measure and evaluate the torque, or we can think of some arrangement by which the torque can be directly measured. So, either measure independently or measure directly. Of course, direct measurement has some advantages, because the errors in measurement of F and R are going to translate into error in the measured quantity, and that can be avoided by measuring the torque directly. So, why do we measure the torque? If you look at the following, if you have a rotating machinery, the torque multiplied by the angular velocity, actually is proportional to, gives the power. So, the reason why we are interested in measuring the torque is of course because we would like to measure the power through that one. So, the point I am trying to get at is that the measurement of torque is directly related to the measurement of power, and this could be in different cases. For example, measurement of brake horsepower or brake power of an engine, which is very common, or measurement of torque produced by an electric motor. So, electric motor is used to run a pump or run some other apparatus, and you require to know the torque produced by the electric motor, and we will have to measure it. are studies on a structural member which undergo torsion. So, torque measurement is required when you have a system where some structural member is undergoing torsion, like for example, a shaft of an engine itself. The shaft of an engine is going to be transmitting power, and during this process it is going to undergo torsion, and we would like to find out whether the torsional stresses set up in the shaft are below the allowable stresses for that material, or how to characterize that. The next one you are going to be interested in is power measurement, and as I mentioned just a little while ago, we have the important case of measuring of brake horsepower of an engine, and you know an engine is always, the specification of an engine is in terms of its RPM, the higher speed it will operate at, and also it will tell you what is the horsepower it will produce. So, this is an important quantity which we have to measure. In a laboratory where engines are being tested, one of the most important things we do is to test for the horsepower or the power output of an engine, and it is usually called the brake horsepower, as we will explain later why it is called the brake horsepower. We may be interested in finding out what is the power generated or produced by an electrical generator, for example. There are various ways of measuring these quantities, and we will look in detail at some of the more important ones. So, we will not be able to discuss everything which about these things. So, we will try to discuss what are all the most important principles involved, and also some of the important or some of the more usual methods which are used for measurement of such thing. So, in order to start looking at this, I thought I would look at a typical example. I have taken it from recent literature. So, typical layout used in engine studies, let me just go through that and see what are the things, whatever we have discussed till now is going to make sense when you look at this. This is a paper taken from the ASME Journal of Engineering for Gas Turbines and Power 2001. The credit is given here by Tennyson Reeds. This is just an example of what all are involved in a typical engine study. So, we have a typical layout. In the slide we show a typical layout used in engine studies, and you can see, let me just go through in some detail what it contains. So, this is the engine which we are now looking at. The study is basically study of this part of the thing. This is the engine, and wherever TC is written, thermocouples are there to measure temperatures, and such a symbol, it is a pressure gauge. So, pressure measurement locations are also given. So, you see that large number of pressure measurements are involved, large number of temperature measurements are involved, and apart from that a few other important things are, for example, you have the smoke meter. There is the exhaust is taken to a smoke meter. We are talking about the opacity measurement, that is one of the measurements which is going to be there. You also have particle analyzer to find out the diameter of the particles, the size distribution, and the number, and so on. So, there is another, of course, we have not covered a discussion of particle size measuring devices. They usually operate on the principle of the scattering of radiation from the particles, and by looking at the scatter pattern of the particles, one can in fact get an idea as to the diameter and the distribution and so on. So, this is the particulate analyzer. Then we have an exhaust gas analyzer, as you can see here. This is the Nicolai FTIR. We have not discussed an FTIR instrument in our earlier discussion. It is a Fourier transform infrared spectrometer. The spectrometer will give you a spectrum corresponding to the species which are present in it, and by looking at the magnitude of this the size of these signals due to each one of the gases, we can find out what are the concentrations. So, you see that you have a gas concentration measuring device here, and of course, there is cooling water coming in and cooling out going out. This is a exhaust gas recirculation cooler. So, some amount of the gas is recirculated. So, this is actually they are studying the engines. In engine studies there are several processes that can be studied, and one of them is to look at the EGR cooler or the exhaust gas recirculation. Then they also have a air preheater. They have so many orifices and so on to control or to measure the amount of various fuel and also the air which is used in the running the engine and so on. Then we have the CO2 analyzer both here as well as here. So you see that typically an engine laboratory, a single engine with so many different instruments attached to it is a major item in any laboratory. It's a very expensive one. It contains a lot of measuring instruments and a lot of information can be obtained by doing the experiment with all these measurements taken simultaneously. In a later lecture we will also look at a similar situation, and we will see, for example, here there are so many pressure gauges, pressure transducers, there are many thermocouples, and there are other devices to measure air mass, air flow and so on. All these require simultaneous measurement. So one cannot of course go on taking readings. In the earlier times we used to do that. One student will take the reading here, another student will take the reading here at the same time and so on and so forth. Now we do not do that. When you can afford to have a laboratory as good as this, you will have a data logger. That means that all this information from various instruments which are shown here are going to be logged in real time using a data logger. That means that you have many channels and all these inputs go into the various channels of the data logger, and the output is recorded almost on a continuous basis with respect to time. And the other advantage of that is that the data can be saved into a computer, and the analysis can be done by using a program which you can develop or available programs, and then you can analyze the data at leisure after conducting the experiment. The experiment itself is conducted in a very short period, and the processing of the data takes place later on. So the reason why I gave this is to show that we have been in the earlier time we have been talking only about the measurement of pressure, measurement of temperature, measurement of flow rates. We have talked about radiation quantities, we have talked about thermophysical properties. Now really we have tried to come together, bring everything together here in one setup where all the elements we discussed in isolation are coming together in a group. So this is a system level experiment where lot of different instruments are used, and each instrument is going to give you a particular reading and how to integrate this. So the idea is to just indicate what kind of a situation will prevail in real life. So with this background you can see also that we will be measuring the power output of the engine and various for example we may operate the engine at various speeds, and how do you do that? You have to run this engine at various speeds and also allow some of the output to vary by loading the engine. That means that we are going to subject the engine to a load. A load is usually applied through what is called a dynamometer, and then with this as the quantities of interest to us, how these are going to affect the various parameters which we are measuring here. The various quantities we measure using these instruments here are linked to the output in terms of the speed and the load it carries or the power the engine produces. So typical layout for engine studies is what is shown here, just to bring out. In fact we could do it from with any other system. This is taken from an engine side. You could also do it for a gas turbine laboratory or a steam turbine laboratory. Everywhere you can have similar setup. So let us get back to force measurement, because we are going to start looking at force measurement as a main activity for the next 10 or 15 minutes or a little longer. So the force may be measured basically by mechanical balancing using simple elements such as the lever. So force measurement can be done when it is not a dynamic situation. When the situation involves for force measurement, it could be through equilibration, or when situation is one of equilibrium. So you balance the forces. For example, measurement of weight of a body or the mass of the body, because we will see later that mass is going to be measured using a balance. So force may be measured by mechanical balancing using simple elements such as the lever, and a typical example is a platform balance where what we are interested in measuring is actually the mass of the object or mass of the body, but we use the forces generated, because in the gravitation field any mass will experience a force proportional to the mass. So, mass times the gravitational constant. So, if the apparatus is very small in size, the gravitational force, gravitational acceleration is more or less constant, and therefore, that does not come into the picture. So, the mass can be directly measured using that. So, let me briefly go through one or two other situations, and then I will discuss slightly in more detail these cases. The second thing I can think of, or one can think of, is the simplest method is to use a transducer that transforms force to a displacement. This is a very common example. After all, force, if you have a force and if it is applied on a spring element, okay, spring is something which we are all familiar with, and the spring element will undergo a change in length, it will undergo a displacement. For example, the spring element may be an actual spring as in a spring balance, or it could be an elastic member that undergoes a strain because of the force applied on it. So, the strain is nothing but a displacement, and the spring element is an elastic member. It may be in the form of a rod, or it may be in the form of a beam, or it may be in the form of a ring. Any of these elements are possible. So, the springiness is because, or the displacement is because the material behaves as an elastic material. When the displacement is when the strain is very small, the material behaves as an elastic material, and the force or the stress is proportional to strain. This is called Hooke's law, which is familiar to us. So, there is a linear relationship between the applied stress and the strain which is generated because of that, because of the springiness of the element. It may be either a regular spring as in a spring balance, or it could be a spring element in the form of a structural member. Another technique which can be used to measure force is to convert it to hydraulic pressure. So, if I have a piston cylinder arrangement, if I apply the pressure on the piston, it will increase the pressure of the hydraulic fluid which is filling the cylinder. You apply the pressure, or you apply the force on the piston, and the force divided by the piston area is going to be the corresponding pressure, and this pressure is going to be the pressure of the hydraulic fluid, and this can be measured by using a pressure transducer. In fact, we have already seen different types of pressure transducers, and we know how to use them. So, a pressure transducer can be used for measurement of force by converting a force, instead of converting it to a displacement as we did in the earlier case, here we are going to convert it to a pressure. It can also be measured by using what is called a piezoelectric transducer directly. So, we will look at it a little later in more detail. When we are talking about mass, when we are talking about force, the obvious thing to talk about is also the acceleration. The measurement of acceleration is, as I said earlier, is very important in many applications, and a few of them we have already gone through. So, it is based on the fact that the Newton's law of motion says that force is equal to the mass times the acceleration. Suppose I have a mass and it is subject to an acceleration, it requires a force to do that. So, by measuring the force and knowing the mass of the system, of course, the acceleration can be calculated. So, there is one way of doing it. The force may be measured by any of the methods we have discussed earlier, and therefore, the force measurement and acceleration measurement more or less are interrelated. For example, seismic acceleration measurement is based on this principle. So, we subject what is called a seismic mass to an acceleration, and this generates a force. This force is measured by a spring which is going to be displaced because of this force acting on the seismic mass. So, the measurement is actually the displacement of a spring, and that is a equivalent to a force. This force is equivalent to an acceleration because multiplied by the mass. Knowing the mass, I can find out what is the acceleration. It is a very simple way of doing it. So, let us look at some of the details of what we just discussed. So, I am going to look at typical cases. One is we will talk about force measurement. Using simple methods, and then we will go on to force transducers and so on. We will discuss some of the issues. For example, I talked about a spring balance, if you take for example. So, this is very commonly used. So, we have a support which is fixed support, and we have a spring, and then we have the W, the weight which is hanging from it, and you can put a some kind of pointer here attached to this the base of the spring, and you have a scale here. This is 0 and maybe this corresponds to 10. So, this is the weight. So, spring balance, what happens when there is no weight here, it will be in this position, uncompressed, unextended position. So, the I have of course exaggerated the extension, it is extending quite a bit here. So, the spring extends. So, spring extension from its initial length. Initial length means unloaded length. When there is no load on it, there is a certain length L, and it extends by a certain amount, and we know that the spring has a linear relationship. Therefore, F is equal to K times X, where this is called the spring constant, and this is the displacement. And what I am measuring, of course, in this particular case, I am this is nothing but the weight of the object which is put in the pan. This is the pan here. Of course, when I said extension from its initial length will mean when the pan is also there. So, the pan may have its own weight. So, you adjust the 0 such that with just the pan it is zeroed, that is the position 0, and then from that onwards whatever takes place is due to the weight of the object which is hanging from the support, hanging from the string. So, if I have a material of the spring, so let us look at the spring, how it is made. So, we have spring has got a certain material, it has got a mean coil diameter of dm. So, just from strength of materials we can work out the spring constant, that is what I am trying to do. The mean coil diameter is dm, number of coils is n, and then we have the shear modulus. Sometimes the symbol G is used for that. I am just using shear modulus ES, and the wire diameter is dW. So, the spring constant K is given by the shear modulus ES multiplied by wire diameter to the power of 4 divided by 8 cube of the mean coil diameter multiplied by n. This gives you the spring constant. So, let us look at the spring constant a little more. So, you can see from this equation F equal to Kx, we can see that this x is nothing but F divided by K, and the magnitude of the displacement is inversely proportional to the spring constant. So, if you want to have a reasonably small value for the displacement, one would like to go for a large spring constant, or another way if we can put it is the following: if we want to measure large forces, we of course will require large spring constant. That means that the same spring balance I cannot use with infinite precision. I cannot use it for measuring a very small force or a very small weight. I cannot also use it for measuring a very large weight. So the behavior of the spring depends on the spring constant, and the spring constant is to be chosen to cater to a particular range of the measured value of the force. If you want very large forces to be measured with a reasonable magnitude for the extension, I will have to choose the k properly to suit that particular application. And also you will see that if you see this force per the F is the force and k is the, so the displacement is proportional to F by k. The larger the spring constant, the smaller the magnitude of x. Therefore the sensitivity is also determined by this F by k. The spring constant is going to determine the sensitivity of the particular spring material. In fact, we can also have spring material not in the point of a, this was a coiled spring. What we showed earlier is a coiled spring made of a suitable material, and usually you should not allow the spring to extend too much because it may undergo permanent deformation. So that is very important. So if you subject it to a load which is too large, it may actually undergo a permanent set, and therefore it becomes a useless instrument. Therefore one has to remember that there is a certain maximum value of force or weight which you can measure with a particular spring. The next way of, the second way of doing the same thing is to use the structural member as a spring element. Structural member as a spring element. This is by far the most common. So we will say this is the most common in practice. So what do we mean by a structural member? So it could be of different types. For example, if I have an elastic element which is in the form of a small length of a rod, so I have one end fixed rigidly and you have a rod maybe it is a circular cross section for example. So I applied a force at the free end. The force is applied to the end which is free, and now what will happen is that because of the force it will undergo a displacement. So this will move slightly downwards, just like in the case of a spring. So this displacement, this elongation if you want to call it, elongation is a measure of the force. So if I have the area of cross section is A, so if the area of cross section is A and the Young's modulus is E for the material of the rod, and if the deflection is Y, that is Y is the deflection or elongation, the spring constant is nothing but area of cross section times the Young's modulus divided by the length, AE by L. You can in fact verify this. A is in meter squared, Young's modulus is in Pascal divided by meter. I can replace Pascal by Newtons per square meter. This meter square will cancel, so Newtons per meter. So F equal to K times Y. K is in Newtons per meter, so it is a spring constant. So for a structural member in the form of a rod of certain length L, area of cross section A and the Young's modulus E, the spring constant can be easily worked out as A by L, and now you can immediately see what is going to be, how you are going to design a simple element like this, a structural member which is in the form of a rod. So, the choice of the material, so you can choose the material because material will determine the material, particular material determine the Young's modulus. So, you can have different values of E there, and for getting different values of K, if I make it a larger cross section area, it becomes stiffer. So, A is the stiffening mechanism, and if you make it longer, so you can see that it is going to become the less stiff. Okay. So, the A by L, the area to area of cross section to length determines the value of K. Once you have determined the Young's modulus or chosen the particular material, the area of cross section to the length, that ratio is going to play an important role in determining the value of K. Of course, in practice we are talking about very small elongation, we are talking about micro strains. In fact, if you remember, when we talked about measurement of pressure by using a tube and the pressure is applied inside the tube and you have a transducer on the strain measuring element fixed onto the wall of the tube, we are talking about very small strains, we are talking about micro strains. So, here we are actually talking about micro strains, we are talking about very large pressures, large forces being measured by using a very stiff member. So, you are going to have very small changes in the elongation. So, to measure a very small elongation, we require a very sensitive measurement device. Let us look at another element which can be used for this purpose. The case is that of a cantilever beam, which is very often used for measurement of forces. So, cantilever beam. So, what we have is a support, rigid support, a long rod of some suitable cross section. You apply the force at the free end, the force is applied at the free end, of course it will bend like this. So, there will be some displacement as it is shown here. Again, in this case, if the Young's modulus is E and L is the length of this cantilever beam, and if the area of the I is the moment of inertia of the cross section. So, this is actually a case of bending, and we know from our study of bending, case of bending cantilever beam or any bending of any element like this, that the moment of inertia of the cross section is going to play an important role in determining the stiffness of the system. So, I is the moment of inertia. So, we will call it the moment of inertia. I am sure all of you know all these things from your course on strength of materials, where you will have learnt about the bending of beams and so on. So, what I am showing is the case of a cantilever beam, the Young's modulus E, the length of the beam and the moment of inertia are going to determine the spring constant, and the formula is K equal to the spring constant 48 EI by L cube, EI by L cube. Again, you see that the moment of inertia is going to determine very clearly, it is the numerator. The longer the length, the less stiff it is. As you can see, it is the length is in the denominator. If you make it longer, it becomes less stiff, whereas the moment of if you distribute the material of the cantilever beam such that the moment of inertia is larger, it is going to give you a larger spring constant. Of course, once we have determined we have chosen the material, we do not have any control over E, and therefore only the geometric parameters, the geometry controlled. The stiffness, when I say stiffness, stiffness means more higher spring constant. So, very stiff means spring constant is large. Stiffness is controlled by the geometric parameter. In fact, it is true in the previous case also, by geometry of the element, of the structural element. So, a cantilever beam can be used. All you have to do is to, in the cantilever beam case, the force is determined by, for F equal to ky, y is the displacement. So, displacement is going to determine again the force. So, force is now, in other words, you can see now for all the examples I have given till now, the effect of the force is to bring about a displacement. So, you can generally say that force creates a displacement, and in our terminology of measurement, so displacement is a measured quantity. So, this is just to highlight that the principle, this is the measured quantity and this is the inferred quantity. So, we are measuring force or inferring force or estimating the force by measuring its effect in terms of a displacement. So, this actually is a transducer, as you can see. You are converting force into a displacement and therefore, it is a transducer. Let us look at one last element. It is in the form of a ring of material, and you can apply the force either in this fashion or in this fashion. You can either compress or extend it. So, it is in the form of a ring under compression or tension. I am assuming that the ring is a small cross section compared to the diameter. Therefore, I will take this as the diameter. Compared to diameter, is very thin, and if we take the diameter of the ring and E the Young's modulus and I is the moment of inertia of the section about its centroidal axis, you can see what is going to happen. If you apply a force like that, if you take a section here, it is undergoing bending. Okay, it is actually undergoing bending. Therefore, the formula which we are going to have is similar to what we had earlier. The K value for this particular case works out to 16 divided by pi by 2 minus 4 by pi multiplied by EI by d cube. So, what is common in all the 3 cases we have considered now, 3 or 4 cases? The commonality is that force is now converted to a displacement and the displacement measured, and from this you work backwards as knowing the spring constant of the particular system, either a regular spring or one of the structural members, we can find out what the force is. We will stop there and we will resume in the next lecture. Thank you.